And you may want to wear earphones if they're noise, by the way. Okay. Let's see. Okay. Yeah, probably less light is better. Okay. Hi. How is the audio and the webcam? Good, good. Okay, and I've got some different people here. We have Amy, Angel, April, Brittany, Dan, Darren, Elva, Hannah, Janan, and Marcos, and Maricela. My gosh, Milo, Peyton. We have Rocio, Rodolfo. We have we have Rosali. Okay, we've got loads of people here. Very good. Okay, and when we look at where we are this evening, you're going to see where we are in the agenda. We know that in this class, we have recently had the second exam, and that's leading us into our next set of 3 chapters. And so we've been working on number 7, and we'll also, of course, work on number 8 and 9. And I just wanted to comment, the Riverside District is on kind of a later schedule than some of the other local districts. And ours goes later into the semester than some. So there's still a good bit of a way to go in our journey. And I know that as we get started, when it comes to practicalities, we want to remember that following a class session, then I post an announcement. I let us know how far we got, what happens, turning in a participation assignment, doing homework. So those are some of the practicalities I always look at. Another thing is with the conferences, they produce a recording. And they only put the recordings on their server for 14 days. So my plan then is to download the recording and to save it in another format so that you can continue to refer to it. And another thing that's kind of fun and exciting for us, if we look at what is being shared here, is that we have some more development on the labs for this course. If you look at modules, I think what you're going to see here, April 27th is complete. May 4th, the video is not complete. We're starting to get some department videos for some of the upcoming labs. So we're certainly good for this week. And again, it's good to know that the department is continuing to look at those. I've gotten a few reports already for experiment number 9. And if we change over to today's agenda, let me go back to that, and we can show kind of where we are. Let's go to this. So my records, what I have from my records, and if you're understanding something different, we have been working in Chapter 5. So this first hour, we would be doing some wrap up on the ideal gas law. I'd like to show the combined gas law as well too, because that's highly practical. And I want to keep student participation in mind as we work together to get some student interaction on all of these things. We'll then discuss Dalton's law and partial pressures before we look at future sections there. And let's go back here for a moment. Okay, let's ask some questions. Can anybody, oh, okay. Let me see. Okay, there should be a sheet of notes. Oh, I see something. Let me make sure that I'm sharing the right thing. The item that I want to share is just a set of notes. Okay, so your notes there. Okay. Okay, you people see notes? Okay, good. So what my notes say is that we are starting from the ideal gas law and then going on to Dalton's law. We actually took a look at the ideal gas law before, and we're continuing on it a bit. Let me get to the right place. These slides, it's unfortunately, it can be very slow to bring up some of the slides. Okay. So from previously, what we had seen is that the ideal gas law allows us to combine the 4 different properties of gases. And we know that the product of pressure and volume is stated to be equal to the number of moles times R and times T. So this is a good point for a small question. Okay, let me take a brief poll. Can you see 7.5 on the screen? That's what you should be seeing at this point. Okay, good, good. Okay, I'm going to ask people the units for each of these quantities that we normally use. What would be the units for pressure, which is the force that the gas exerts on the walls of its container? Pressure is usually measured in what units that we saw last time? Okay, good. Yeah, you'll see that with based on our units of R, we want to do that in atmospheres. And we also know how to convert between atmospheres and torr if we need to. So now you know what I'm going to ask next. What about our units of volume? Volume hint. Think about a bottle of something about this big. volume for the ideal gas law is measured in, okay. So I heard Berto, that would be good for atmosphere. Okay, for pressure. Okay. Now let's look at something. Let's look at this part here. And another thing is countries in Europe use it for measuring volume. Okay. What units do you see corresponding to volume in the ideal gas law? Units of... Okay, good. Right. Okay. Now, what does N stand for? N stands for the number of... Something that measures amount. It's also a furry creature. Moles, good. Okay. Now we see on the slide that R is the universal gas constant. And based on the units that we normally use, we usually use that in liter atmospheres per mole Kelvin. That's what we do there. And let me see. Now, I have both an easy question and a hard question. Temperature. What are our units for temperature when we're working with gases? Good. Okay. Now, the Kelvin temperature scale is absolute. And we need an absolute temperature scale because of Charles' law. Okay, I have a question for you. When temperature approaches zero, what should the volume of a gas be? Because we know that a volume decreases in volume as it gets colder. So as the temperature gets colder and colder, that is, it goes to zero. Well, let me see. Now, we are saying that 273 K is standard temperature, but what we're saying here is what if what happens to the volume of a gas? As temperature goes to zero, volume goes to... Good, good. That's what we mean by an absolute temperature scale. It has to have the property that the volume goes to zero as temperature goes to zero. Now, does the Celsius scale have that property, that the volume of a gas is zero at 0 Celsius? Right. We can't use Celsius or Fahrenheit for that reason. Okay. And if you would please tell me what the conversion is. If we had a temperature in degrees C, it's easy to convert it to Kelvin. So what do you do if you want to go degree C to degree Kelvin? You want to add... Right. Okay. So again, those are some of the things that we're doing with the ideal gas law. And from last time, we saw that there are problems that you can do where you rearrange and you solve for pressure, you solve for volume, you solve for number of moles, or you solve for temperature. Now, there's another thing too. Let's see if I can share a whiteboard for a moment. Let me bring this up here for a moment. If we look at the ideal gas law, now let's make things a little bit bigger here. If we look at PV equals nRT, I may have mentioned before that if you consider two sets of conditions, and we let the number of moles be constant. So the way that we would write this up is to say that under your first set of conditions, we're going to write P1 V1 equals nR T1. That's my first set of conditions. And under a second set of conditions, I would then write P2 V2 equals NR T2. And you'll notice I'm dividing one of those equations by the other. I could look for things that are the same top and bottom that we can cancel out. And if you were to go ahead and cross multiply these, see, and you're going to then go ahead and do a bit of rearrangement. You get a variation of the ideal gas law, which is called the combined gas law. And the combined gas law is really pretty easy to remember. We often use the combined gas law to convert gas volumes to standard conditions. And before we derive and state the combined gas law, let's talk about STP. Everybody, what does STP stand for, at least when it comes to gases? Okay, so standard temperature is 0 degrees C, which is about 273 K. And we also know, of course, that just trying to give myself a lot of light. Light is good here. Okay, and standard pressure, of course, is 1 atmosphere. So going on here with the combined gas law, let's go ahead. And what you're able to write here is P1 V1 over T1 is equal to P2 V2 over T2. Interestingly, when using this law, one thing that I would point out here is that you don't have to use the standard units of pressure and volume as long as they're the same on both sides. You do have to use temperature in Kelvin in order for it to make sense. So what I'd like to do for a moment is this. I would like students to give this a moment to try the following problem, and then we will compare. Consider a situation where you have a first have a pressure. We'll try to keep the numbers really easy here. The pressure of 2 atmospheres, volume of 10 dot liters, and temperature is 300 dot K. Second situation. Okay, let's change pressure of 4 atmospheres, volume of 20 liters. What is the temperature? Let me have you guys give that a try. Let's take a couple minutes to try that. It's fast. Let's take a look. That could be. Okay, so yes, some people solve the formula first, others just plug the numbers right in. And if I were a little bit more careful, I'd be showing all the units and everything, but I want to kind of make things easy. So let's put that this is 2. This is 10 with a decimal place. And this one is going to be 300 decimal place. Okay, and in this new situation, this one is 4 atmospheres. This is 20 dot. And this one is unknown. So if we do a little bit of cross multiplying here, let's go and do this. We're going to be doing here 2 times 10 times T2. Is equal to 4 times 20 times 300. Okay, we have to divide both sides by 2 and by 10. And you can see that I chose these numbers kind of strategically. So if I go ahead and cancel, 20 cancels 2 and 10. Now let's see. I just want to make sure everything is done correctly. So what are you getting at this point? Let's update what we were saying with that. Well, let me see if that's the case. Let's try and reason through it for a moment. Okay, the pressure increased by a factor of 2, so that should double our volume. Yeah, okay, right, that's correct. Yeah, because the pressure increased by a factor of 2, with other things equal, would double the temperature. And then another thing that happened, let's see, is the volume doubled. That corresponds to a doubling as well. Yeah, okay, so it was 300, double, and double, 1200. That's right. Good. Let me take questions on that. No, I would say that a lot of the times, by the way, with the ideal gas law problems, my students usually like them. They, they're kind of, going by formula, which is one of the interesting things here. So again, you can use the combined gas law anytime your sample stays constant, but you're changing up the conditions. And let me just remind you of one other thing about calculations before you go on. I have also mentioned that when you do gas law calculations, we often work at standard temperature and pressure. So let's see if you can recall the following. Under standard conditions, how much volume does 1 mole of a gas occupy? It's a good number to remember. It's called the molar volume of an ideal gas. Good, good. Okay. And if you ever have any problems involving moles and amounts, that's convenient to remember. So again, very often we'll convert the volume of a gas to standard temperature and pressure, and then we use the 22.4 liters per mole. Okay. So as I look at who's here, wow, that blew up for a second. Hello, Wendy, Yair, we've got Vanya, Vanessa, Valerie, Shaylin, Sandra, lots of people here. So I just wanted to mention everybody who's here. And let me see. Okay. It's probably a good time here to go on to our other major gas law. And this one is due to Dalton, that same Dalton who did all our atomic theory and cool stuff like that. And my note to you is that you want to start thinking about Dalton's law whenever you hear something that indicates you have a mixture of gases. And I guess you could say when you have a mixture of gases, they kind of behave like people in social isolation, right? You know, this social distancing that we're having. Okay. Do individual people interact much if we socially distance them? The answer is right. So it's kind of the same thing with Dalton's law. Dalton's law is saying that the properties of gases, what we call the partial pressures, the individual pressures of gases, that they're behaving independently of one another. So what Dalton's law is saying is, say you have a total pressure, and I should mention, if you have something that's open to the atmosphere, the total pressure will happen to equal the atmospheric pressure. So for example, you're doing a gas under ordinary conditions, it would be at atmospheric pressure. So you add together the pressure of each of the gases individually, like the pressure gas 1 and the pressure gas 2 and the pressure gas 3, and however many you have. So it's a pretty easy and straightforward rule. And again, it comes from the fact that these gases are kind of doing their own thing. They're behaving independently of each other. They exert the same pressure that they would if they were if they were separate. So let's look at something here. And there are lots of gas law. There are lots of gas problems that have to do with Dalton's law. Let me see, for example, if I have some that I can show you here. One moment. Okay, I'm going to be showing an example in just a moment. Yeah, let's go here. Okay, so we switch over here to an example of Dalton's law. Everybody take a moment to breathe out. Okay. When you exhale air, what is air made of mostly? Air is mostly, well, let's see. Now, you do exhale out some CO2, but the air around us is mostly nitrogen. And we also have, of course, oxygen. We couldn't breathe, we couldn't survive very long without the oxygen in the air. And there are smaller amounts of CO2 and water vapor. In the process of respiration, we produce carbon dioxide, gas, and water vapor, and we do breathe them out. So in this problem, suppose you have a sample of exhaled air. We are assuming here that the amount of nitrogen gas is 563 millimeters of mercury. And question, is a millimeter of mercury the same thing as a torr, by the way? Oh, it is interesting. Yeah, yeah. And what I find interesting is that people respire, they breathe out CO2 and water, which are the same as the products of combustion, so. Okay, just a sec. My son has something just a second. Just a sec. Okay. And what I was going to say here is that in this particular example, say that you have 563 millimeters of nitrogen, 118 of CO2, of O2, 30 of CO2, and 50 of water. To find the total pressure of the sample, all we have to do is to add them together. So that's a very simple example of Dalton's law. I'm sure you would agree. About the only thing that you have to do for this problem is just to make sure that everything is in the same units. Now, I would warn you that I have seen some Dalton's law problems where it's not quite so straightforward. So I'm going to give you a different problem here. And let's make sure that I am making my letters nice and large. Suppose an experiment is conducted at an atmospheric pressure that would be funny spelling, atmospheric pressure of 1.05 atmosphere. Hydrogen gas is collected by downward displacement over water. At this temperature, the vapor pressure of water is 18 torr. Okay, so my question for us here is going to be for us to find the pressure of dry hydrogen gas. So let's take a moment. Okay, let's try something. Let's see if the audio is working. How about now? Oh, okay. Okay. Students, let's look at the statement of the problem. Okay, good. Okay, so again, let's review this for a moment and think about how we would use Dalton's law for this. Our experiment is conducted at an atmospheric pressure of 1.05 atmosphere. So remember, if your experiment is open in the atmosphere, it'll normally be at atmospheric pressure. Okay, let me see something. Okay, let's try something. Yeah, I think there's just a bit of a delay. Okay. Oh, I see something too. Let's do this. And I think I'd like to move this over here. Okay. Do you see the webcam? Okay. How about audio? Okay, good. Okay. Tell me about the steps you would need in order to solve this problem using Dalton's law. yeah. And I think what I'm going to do here is I think I see what the problem is. It seems to me like the PowerPoint is what's slowing us down. It seems to me that the PowerPoint, which is online, is kind of taking up a lot of bandwidth. So let's go to the shared notes for a moment. I'm going to give people a Dalton's Law problem to work. Suppose an experiment is conducted at an atmospheric pressure of 1.05 atmospheres. Hydrogen gas is collected by downward displacement of water. At this temperature, the vapor pressure of water is 18 torr. Find the pressure of dry hydrogen gas. Okay, so as I look for your comments, right. And students, what I think I'm going to do here is I think that if I use something in this PowerPoint form, it's just too bulky. So everybody, did you know too that you can also type in the shared notes? Students, I think something I'm going to do too. I'm going to convert my notes to PDF format because that makes them faster. But let me ask everybody, see if you can type in the shared notes. Oh, good. I see a few things. Students, what do you notice about units in this problem? What would you do there? What should we use, atmospheres or torr, do you think? Okay. Let's have a student convert 1.05 times 760 and type that there. It should be a little bit more than 760, right? Good. Okay. Why don't you write that is equal to just write equal hydrogen plus 18 then, right? Okay. And let's take the difference. Okay. Let's have a student find the difference between the two. So if you have 798 and the other side you have 18, what are you going to have? By the way, it looks like the PDF is working a lot better here. Could I have a student type the answer in the shared area? Good, good. Okay, right. And keep in mind that it could be the case if you have homework or if you have an exam or something too, it might want you to change between different units. So let me see students respond. If I could ask here, what's the relationship between atmospheres and torr then? If you needed to convert between one and the other. I'm going to catch up with the notes here. Let's call in some different students. Amaya, could you type in the relationship between atmosphere and torr? Okay, Jeanette has it. Good. Okay, so if you wanted to convert 780 to atmospheres, what would you get? Good, good. Okay, let me double check that. It might be a little bit low. If I take 780 divided by 760, okay, yeah, let's make it 1.03. Good. Okay, very good. Okay, let's take questions from students. And keep in mind that what we're about to do is to finish what we're doing with the gas law part, and we'll be starting to talk about some of the intermolecular forces. That's going to lead us to talking about solids and liquids because, okay, now let me see, by the way, if you guys have my webcam on. Okay, you can see that I work with two computers to make things easier here. Okay, and okay, what did we say earlier about gases? Are the gases having a lot of forces between them, or are they kind of doing their own thing? Are they solo, or do they have relationships with each other? Gas particles tend to be, are they loners or couples? Okay, good. Yeah, they're like people in Alaska. They don't see. Yep, that's right. Okay, so gas particles are loners, but we know that the gas state of matter is not the only state of matter. If we have states of matter where there's stronger forces drawing things together, then we're going to get liquids and solids. So to understand a little bit about the relationship between gases, liquids, and solids, say that you had a gas. What would tend to happen to a gas if you put pressure on it and or you cooled it down? If you put pressure and you make it cooler, the gas can turn into a... Okay, good. Now, you could, if you were to remove still more heat and compress it so you can have even better forces, you're going to make a solid. And that's what we're going to be looking at here as we go to our next topic in Chapter 7. In looking at intermolecular forces, we would not have any solids or liquids if we didn't have forces between molecules or particles. You and I wouldn't exist. No living things would exist. To my understanding, there are no living things that are strictly in the gas form. You have to have liquids and solids in order to have living things. So, again, the existence of liquids and solids depends on having forces among particles. And that's kind of where we're going to right here. Intermolecular forces are attractive forces that cause molecules to be interacting with each other. Now, I should say the forces inside a molecule are much stronger than the forces between molecules. But the forces between molecules, intermolecular forces, are important too. Let's draw a... do we have audio now? Let's check something. And one of the things that I want to do... Okay. Well, let's check something here. Okay. Let's see. We could do a poll. Let me see if I could start a poll. Okay, here's the poll. And what I'd like you to do in the poll is say, yes, you have audio, or no, you do not have audio. So there's going to be a poll there you can respond to. Okay, good. Okay. All right, let's see if everybody can respond. And Pamela Kimbrough is going to say yes. Okay, good. Okay, let's see. Let's see. Okay, so far we have 16 and 4. Good. Refreshing is often a way to restart the audio. Other things I could think of is make sure your computer is not bogged down. You can always exit and re-enter. If students have any other suggestions, let me know. Okay, and it could be a lack of audio, could be due to delay too. Let me see. Any other suggestions or comments that we could bring up there? Let me see what I can do. Keep in mind, in mind there will be a recording. Okay. I do want to see if I can show something here, which is the first kind of intermolecular force that we want to look at. And I want to start with a picture here. Okay. Now, if you see me, I look at my other computer too, so that I'm keeping track of what you guys see. I'm going to refresh my other one. Okay, what I'd like you to see on screen says 7.7, and it's going to show how London dispersion forces develop. You may see those arrows. Let me ask. Well, I see what's happening. Maybe I'm sharing the wrong thing. I'm going to share the right thing. Okay, what you should be seeing here is called London dispersion forces. And we have a picture here of, I think it may be easier, by the way, if I dispense from showing the webcam at the moment. I think that the webcam may be slowing us down, so I'm gonna leave that off for the moment. What I wanted to show you here with London dispersion forces is if you have two molecules next to one another, even if those molecules are nonpolar themselves, sometimes your electron density is a little bit unbalanced. You'll have more of it on one side of the molecule and less on the other. Now, what happens is that the partly positive part of one molecule lines up with the partly negative part of another. And it forms just like a really brief little interaction between them. And tell me, everybody, what are the particles that are responsible for this force? What are the particles that are feeling each other or interacting with each other? Hey, Dan, good. Okay, so those particles are electrons. Very good. Yeah. So London dispersion forces result from the fact the electrons are unevenly distributed for just a very short period of time. And it actually induces a dipole in neighboring molecules. And these molecules get these short-term interactions between each other. An important thing about the London dispersion forces is the more electrons in a molecule, the more London dispersion forces. This also correlates with higher molar mass. A molecule with higher molar mass will also have more electrons. And we can see more about that. Let me see something here. I may have a slide that helps me kind of show that. Here's something that I'm going to show here. Okay, I'm going to be taking a look here at our periodic table. And do you see the periodic table here? Okay, good. I'm going to focus for the moment on, let's look at the noble gases. If you look down, you have helium, neon, argon, krypton, xenon, and radon. it is observed that helium has a very, very low melting point and boiling point. And it boils at about 3 to 4 degrees Kelvin. But radon has a much higher boiling point. In fact, it is possible to make solid radon. Let's see if we can explain why that is. I may be able to turn on my webcam again. Let's look at that for a moment. Okay, so let's look at the difference between them. Who's going to have more atoms? Or pardon me, who's going to have more electrons? The one that's going to have more electrons is the radon. Yeah, it's element 86. It's going to have 86 electrons. Helium only has 2. With those helium molecules, there are only 2 electrons. The chances that you'll have both of them on one side and not on the other, not very probable. If you've got 86 electrons, though, there's a lot of opportunity to build up London dispersion forces. So the melting points and boiling points of the elements in the periodic table, they are going to increase with your molar mass. Okay. And you could expect to see similar trends down the other groups of the periodic table as well. And there is something that I wanted to mention with London dispersion forces, the first of our 3 kinds of intermolecular forces. And let's see if my shared notes will come up here. And the important thing here is that all substances have London dispersion forces because all substances have electrons. There's no such thing as something that doesn't have electrons. So London dispersion forces are the weakest kind of intermolecular force, but all substances have them. And again, they even operate in the noble gases and nonpolar compounds. So questions so far. And I just want to mention, some people call them van der Waals forces, but London dispersion forces, van der Waals forces, that's the same kind of thing there. So just want to mention that in case you run across that. Just changing this up a little bit. And let's go to our next kind of intermolecular force. And okay, we want to make sure I have my notes here. Seems to work much faster, I think, with PDF. Okay, there are 2 other kinds of intermolecular forces that you need to know about too. And in addition to the London dispersion force, the next one that we need to learn about are called dipole-dipole interactions. And dipole-dipole interactions occur if a molecule is polar. And a polar molecule, let's see if I can show something. In a nonpolar molecule, everybody shares the electrons equally. But in a polar molecule, one part is more negative and the other part is more positive. We learned before that we can have polar molecules if you have polar bonds and if the molecule doesn't somehow cancel that. Remember that there are some shapes that will cancel polarity. So let's look a little bit further at this. I have a slide here that's about a molecule you may be aware of, just for the fun of it. Let's see what you know about formaldehyde. Yes. Would be right. Sure, anything would, yeah. I see what you're saying. That's the one case, right? Okay, I see that one case because a proton, well, it's a proton though. Let me think about it. I guess you can't say, because the proton is an elementary particle that doesn't contain an electron. So Milo, let's perhaps put it this way: if you had an atom or a molecule, it would. But yeah, a proton, an H plus is actually an elementary particle that's not an electron. So right, if we take that level, I see what you're saying. Okay. Okay. Let's look at dipole. What is formaldehyde used for? Mm-hmm. Right, because formaldehyde is used in water solution to preserve samples and to preserve bodies. And when you look at the structure of formaldehyde, we're going to see some more about formaldehyde when we do chapter 20. Now, another interesting thing you might not know about formaldehyde is new carpet smell. A fresh carpet smell in new buildings is due to formaldehyde as well. So let's look at something here for a moment. Let's see how these formaldehyde molecules are interacting. When we look at the molecule, we know that oxygen is more electronegative than the other part of the molecule. So you'll notice a partial negative charge. This part is partially negative on oxygen and then partially positive on the other part of the molecule. Well, it's going to tend to get together. The positive and negative parts of different molecules interact, and they give a dipole interaction. Remember that forces are stronger between polar molecules than between nonpolar. So everybody, which is going to be stronger, your London dispersion or dipole? Which one is stronger? More charge, stronger. Good. Okay. Now, our last kind of intermolecular force, and we'll be taking a break soon, last kind of intermolecular force is actually a stronger form of dipole force. And I can help you remember this with a funny saying. In the movie E.T., E.T. is told to phone home, and I'm going to spell it a different way. And this helps us remember that hydrogen bonding occurs when fluorine, oxygen, or nitrogen on one molecule is attracted to hydrogen on another molecule. You'll see those hydrogen bonds where they have those little broken lines. We're showing kind of an interaction between those two molecules. And what molecule are we seeing on the screen? This is a molecule for which hydrogen bonding is very important in influencing its melting and boiling point. This is a molecule that has an unusually high melting and boiling point for its molar mass, by the way. And it's a molecule that's familiar to all of us. On the screen, we are seeing H2O, right? Yeah. The properties of water, which we're going to continue to explore in this chapter, are very much due to hydrogen bonding. In fact, in solid water or ice, the hydrogen bonding creates kind of an open structure with low density, and that's why ice floats on water. Now, water is not the only substance that can undergo hydrogen bonding. There are other molecules such as hydrogen fluoride or ammonia. Let me see some others. Are other examples. And hydrogen bonding becomes very important, not only organic chemistry, but also in biochemistry. If you study the structures of different organic molecules, like proteins, hydrogen bonding is very important to their properties. On a kind of fun note, if any of you have hair that's chemically treated, that is permed or straightened, that process breaks hydrogen bonds, disulfide linkages, as they're called in the hair, and then they're set in new positions. And that's how you can change whether your hair is curly or straight. So it has to do with hydrogen bonding. So in terms of things that you might need to know about hydrogen bonding, say for an exam or something like that, kind of a summary as we take our break. The three kinds of bonds vary from weak to moderate to strong. London dispersion occurs in all molecules. Dipole-dipole are going to occur in molecules which are polar. But the strongest is to phone home, that is to have fluorine, oxygen, or nitrogen interacting with hydrogen. And hydrogen bonding will really increase the strength of the forces when you look at that. Okay, so at this point, let's take a 10-minute break. Okay, and then back. Okay, so you guys can, check messages or things like that, but we're going to take a 10-minute break. Okay, and I'll be back. Let's see if people have been typing or some things. Okay. I think it would be fun to use a breakout room for a moment. That's something I've been interested in playing with for a moment. So I am going to create some breakout rooms. Let's see how many I want to do. I'm going to make 6 rooms. Okay, we're going to do something really interesting for a second. Take a couple minutes in your breakout room. See how many examples of phase changes you can list among solids, liquids, and gases. So give that a try for a moment, okay? And later today, too, I think I'm going to have some students draw on the board for fun. Just going to say hello to everybody.
You are currently the only person in this conference. Let's have students text your examples of phase changes. Let's see if there's audio. So for example, you might write down, for example, that, okay, freezing, good. And I wanted to show you guys something. On the side, you have this little menu that comes up with tools like text. And let's say you choose text. You can open this up and you can start writing text in there. Yeah, and you have a freehand tool. I think one of the things you're going to find too is I tend to use text a lot because it's freehand is not as easy as it seems. Unless you have a touchscreen computer, it can be awkward. Okay, so freezing is from liquid to solid, good. We put ice in the freezer, and let me see, liquid to, how about liquid to steam, evaporation? Okay, what about solid directly to gas? That's called it's kind of Freudian, sublimation, right? Okay, so let's summarize. Gas to liquid is boiling. I'll take this onto another board here. Okay, some things about this. If we take a liquid and turn it into a gas, that's called evaporation or boiling. And notice that you have to put energy in order to get something to evaporate that. So for example, if you wanted to evaporate water, you would have to make it, you'd have to heat it. You'd have to make it absorb heat. Now, the reverse of that process, if you go from a gas to the liquid, it's going to release heat to the surroundings. So notice that these processes and their energy changes are the opposite of each other. And certainly, I'm sure that these are familiar to you. Okay, so let's look at some others too. Let me see, freezing, melting, all of these are different kinds of phase changes, right? Okay. Now, how do we accomplish this? We change, what variable could we change in order to change one state into the other? There's one that's obvious, but one that may not be so obvious. We change the pressure and or temperature, right? For example, by increasing pressure, you could turn a gas into a liquid and then a solid. Another thing you could do is you could take away heat, right, to make it, okay, good. Okay. And I wanted to point out too, as we start to talk about liquids and solids are sometimes called the condensed phases of matter. Let's mention another important property here. I'm trying to get to another bit of slowness here. It says an error has occurred with screen sharing. Students, I am going to refresh my screen. Hello. Okay, back. Okay. If we go a little bit further with these ideas, I also wanted to mention that we have a related concept called vapor pressure, and this has to do with liquids and solids. So let me go to that for a second. Okay, and vapor pressure is the pressure of a gas that's at equilibrium with a liquid. What happens with vapor pressure is that, let's make sure that we have some webcam here. If you look at the vapor pressure of a liquid, consider a liquid, and a few of the molecules will have enough energy to jump into the gas phase. And you can see these molecules on top there. Now, from time to time, they may collide with the walls of their container and lose a little bit of energy and go back to the liquid phase. So if you get kind of a balance between them, that's called the vapor pressure. And the reason I'm mentioning vapor pressure here is the boiling point of a liquid is when is the temperature at which its vapor pressure is equal to the atmospheric pressure. So again, that's important to recognize. The vapor pressure of a liquid increases with increasing temperature. Okay. And I have a quick discussion question. Compare a polar and a nonpolar molecule. Which should have the higher vapor pressure at the same temperature? Good, good. Okay, because if it has, yeah, Darren, what we're going to say is if it has weaker forces, it's easier for it to get in the gas phase. Very good. So a nonpolar substance like hydrogen or helium, it's going to have a high vapor pressure. Something like water, which is polar, it's not going to be as much. Good. Okay, continuing a little bit with these ideas. Let me, I'm going to take you to a different screen in just a moment. We're still in chapter 7. Okay. Yeah, there's a way for me to go from one to the other. Here it is. Okay. And so one of the things that you would want to know for exams is that vapor pressure is one of the properties that has to do with intermolecular forces. If intermolecular forces are strong, they tend to remain in the liquid form. But if the intermolecular forces are weak, they tend to be in the gas form. We see this if we see the picture of water. Quickly, everybody, what about water? Is water polar or nonpolar? Now, by the way, I'm going to be in the conference on this one too, because I want to see what you guys are seeing. Okay, good. Okay, so what would you predict then about water? Should it have a low or a high vapor pressure? Okay. Well, let's think about it. The forces are strong, so the vapor pressure should be low. Okay. And mathematically speaking, a relationship where if one thing is high, the other is low, is that called direct or inverse? A relationship, one variable is high, the other is low, direct or inverse. That's going to be good. Okay, so water is a polar molecule, strong forces, and it will have a relatively low vapor pressure. But let's look too at methane, which is also called natural gas. Methane is a nonpolar molecule. The intermolecular forces are weak. There's no dipoles there. So what state does methane normally exist in? Hint, it's produced by flatulent cows. Notice that methane is usually a what? Gas, okay. And water is normally a what? Okay, good. So we're seeing these concepts come together. So what are you noticing about forces, by the way, in solids, liquids, and gases? Which one has the least forces? The one that has the least would be the gas. In the middle is the liquid, and the strongest forces, by the way, should be in the what? In the solid. Good. Okay. Now, so you should know some things about vapor pressure, and there's also some other properties of liquids that you should know. Viscosity is how much a fluid resists flow. And if you've taken your car to the mechanic, you know that the viscosity of your engine oil is a very important variable for it. And there is a highly viscous liquid that people like to have. Some people like to have with their morning breakfast. If you go to a coffee shop, what sweet substance might people have at breakfast that is very viscous? Honey and pancake syrup. And I should mention the molecules in something like honey or pancake syrup tend to be complicated. They tend to have high molar mass and a lot of branching. So yeah, liquids with lots of forces, high molar mass, complexity, pancake syrup, honey are good examples of viscous liquids. Okay. Compounds, a liquid that feels thick, that has strong intermolecular forces, large molecules tend to be viscous. And on a related note, let's consider the concept too of what's called surface tension. Okay, and let me see if I can mark this up, by the way. What we call surface tension is how much something spreads out. And if you were to look at a water droplet, I don't know if you've ever wondered about why it is that a water droplet is spherical. Well, what happens is that water molecules are polar and they tend to interact favorably with one another. That's why they tend to adopt a shape where the molecules stay together on the inside, and you minimize the area on the outside. The spherical droplet helps keep those favorable interactions going. And so water has strong forces because of its hydrogen bonds. What does the picture show us about water? What does the picture on the right tell us about water? The ant is doing, or the insect is doing something holy here, right? It is. Let me see if I can change my layout. Oh, yeah, let me see if I can do that.
Go like that. Let's try this, by the way. Let's see if we can make our screen easier to look at. Okay. Can we see better now? Oh, okay. This insect is able to walk on water. Pretty cool, right? Good, good. Okay, Brittany, you've got it correct. What happens here? Water has a high surface tension, and surface tension means its resistance to spreading out. This water doesn't want to be disrupted. It doesn't want those strong bonds to be disrupted. And these interactions are strong enough that they're holding the weight of that insect, right? Let me turn this off so you guys have a better view here. Okay. And let's exit full screen for a moment. I'm going to share the screen again in a moment. Okay. So let's ask a question here. Compare liquid water and liquid, what are we going to do here? Liquid mercury. Okay, which one should have, okay, I apologize, that's not the best comparison. Compare liquid water and liquefied methane. Which would have a higher surface tension? Okay, good. Yeah, because it's polar, and it's polar would have higher forces, higher surface tension. Let's draw together what we've said so far. We've been, when it comes to intermolecular forces, strong intermolecular forces are correlated with a lower vapor pressure, higher surface tension, higher viscosity. And I believe that we have at least a couple more properties that we still need to look at. Okay. And from what you've seen here, these are some of the kinds of discussions that we have in this chapter about the properties of liquids. I would warn you that it's hard to have a very easy, convenient way to describe liquids. In this chapter, we describe some of their properties, but there isn't too much theory behind
liquids and how they're arranged. We can say that with liquids, they certainly have stronger forces than gases, and they're more dense than gases. They obviously have more fluidity than solids. And they have more ability to move around than solids. But if we move into a discussion here of the solid state, solids are our most compressed forms of matter. Please give me some examples of solids. Some common substances that exist in a solid state. And by the way, I think I'm going to move to a different computer. Just a moment. Okay. Hello. Hello. Okay. Let's try something here. I like that. Okay, good. Okay, so we're going to learn some more about those properties here. Get lower down. The board will be up here in just a moment. Okay, so here we go with the properties of solids. Okay, a few things to know about solids. Solids can be crystalline, like table salt is. Crystalline has a very regular arrangement. And the reason that something like sodium chloride has a regular arrangement is that you have your chloride anions, and each one of them wants the best possible interaction with the cations. And they're going to pack or arrange in a very regular structure to maintain this. So crystalline means that you have a regular arrangement of particles.
And by contrast, amorphous. Amorphous means that it doesn't have any regular kind of structure. And a lot of things like waxes, candle wax would be a good example of something that's an amorphous solid. And as we conclude this chapter, we're going to learn that there are 4 basic kinds of crystalline solids. Depends what kind of particles you have. And we're going to kind of meet each of these. Okay, so here is your first one. Okay. Let me see. Where do we see NaCl, which is an ionic solid, as you can see. Okay, everybody. Don't worry, we're almost done with chapter 7. Where have we seen sodium chloride? Is it too obvious? Okay. Sodium chloride. Okay, good. Yeah, we see it at the dinner table. Okay. On a related note, another well-known solid is potassium chloride is a substitute for sodium chloride. And some interesting things about ionic solids that we need to know. Because you have these charged particles and they attract each other, salts, ionic solids, also called salts, have very strong forces. They have high melting points and boiling points. They tend to be hard and brittle. In fact, the higher the charges on your ions, the higher the melting and boiling point. By contrast, a molecular solid has weaker forces. And water molecules are a good example of a molecular solid. Now, water does tend to have a regular arrangement of particles, but how does the melting point of water compare to that of sodium chloride? Think about it if you've ever been able to melt or boil sodium chloride when cooking at home. Is that even possible? Things here. By the way, I'm trying to make sure that you guys can have a good view. Okay, good. Right. So this tells us forces are weaker and you have lower melting and boiling points. The best plans. Let's try this instead. Okay, and our 2 other examples here. There are some kinds of solids called network solids. And the network solid you're seeing here, silicon dioxide, is a major component of sand, like sand on the beach, and also glass is made of silicon dioxide. So this one, you have a lot of strong covalent bonds holding the atom together. It's like a great, huge molecule. And because you've got a lot of bonds there, network solids tend to have some fairly high melting and boiling points. Yes, but that has to do with solution properties. Yeah, that's going to be a colligative property, so it has to do with solutions. Yeah. Yeah, let me see. For network solids, so O2 is an example, but so is diamond. Diamond is a network form of carbon. So is graphite. Students, Roberto, Brittany, others, where do we find graphite, by the way? Where do we run across graphite in our everyday life? Okay, good. Yeah. Graphite is slippery, so it can be used as pencil lead. What we call pencil lead is really graphite. And graphite is also used by locksmiths because it's a lubricant for locks. Helps them open locks. Okay, so so far we've seen the ionic, the molecular, and the network solid. And we have one other kind, which is a very common kind of solid. If you have a metallic solid, you have the metal cations, you have the nuclei, and they have electrons that are kind of moving fairly freely in the metal. And this is why metals are good conductors of heat and electricity. The electrons are mobile and they can move around and conduct. So obviously there are lots of different metallic solids, whether it's copper or aluminum or iron. Any kind of metallic solid. This electron C, as it's called, actually has some pretty strong forces. So most metals have some fairly strong forces. Let me write that down again. It's called the electron C. You've got electrons running around. They don't really belong to any particular nucleus, but they're kind of carrying charge there. And let's see some other things that we might need to know from this chapter as well. Yeah, those, by the way, were the crystalline solids. We can also have amorphous solids, so let's make sure to discuss those for a moment. The word amorphous means without form. And if you have an amorphous solid, we're saying that there's no sort of regular arrangement of their particles. Some of them are formed when liquids cool quickly and cannot form crystals. Very large covalent molecules that can't line up do also tend to form amorphous solids. Rubber, waxes, glasses, glass when it's been liquefied and then solidified, and plastic can be amorphous solids. Okay. How would the melting and boiling points for an amorphous substance compare to a crystalline substance? Think about the interactions there. Just a second. I want to see if I can get this arranged a bit better. Think about something like candle wax or petroleum jelly. Is it hard and brittle with strong forces, or what do you think? Good. Amorphous solids have relatively weak forces. Low melting, low boiling. Okay. And our book kind of leaves things there with the with their discussion of solids, and concludes the chapter by looking at the energy involved as we transition between liquids and solids and other substances. So I just wanted to give you the heads up that having described some of the properties of solids and liquids and everything, we're then going to focus on the role of energy with solids, liquids, and gases. And I need to get to the right part of the presentation here. Okay, I'm actually going to do this part first. So to finish the chapter, we will discuss energy. I'll first explain how to find the energy for a phase change, and then explain the energy change for a change of temperature. Let's go to something here. I should have an eraser here. I'm going to go to something else here for a moment. Yeah. Okay. When we're looking at phase changes, what you want to remember is that if you take liquid and you put in energy, you can vaporize it. You can turn it into a gas. You can vaporize or boil it. And we can also discuss the reverse process, because the reverse process is, let's make this a little bit bigger here. The reverse process is called condensation, when you take a gas and turn it back into a liquid. Notice that vaporization requires an input of energy, and that condensation gives a release of energy. To make these calculations, we're going to have to know a quantity called the heat of vaporization, and that's where we're going here on the next slide. The heat of vaporization, I usually prefer to give it in kilojoules per mole. And for water, the heat of vaporization is a constant that you could look up if needed, and it takes 40.6 kilojoules per mole. So each time you want to vaporize a mole of water, it really takes a large amount of energy. You've got all these forces that have to be overcome for the water molecules. Let's ask a simple question. If evaporation of 1 mole of water takes 40.6 kilojoules, how much energy is needed to evaporate 2 moles of water? Okay, good. Okay. How much energy would be released
if we condensed 2 moles of gaseous water back to the liquid form. Just setting my alarm here. We'll probably go until about 8:15 here. Okay. Okay. And Darren and Jadan are typing. Well, let's think about this. Okay, we would absorb 81.2 if we go from the liquid to the gas. But if we went back the other way, see? Okay, you would release 40.6 kilojoules for 1 mole. How much would you release for 2 moles? Good. If it takes 81.2 kilojoules of energy absorbed to evaporate 1 mole of water, pardon me, 2 moles of water. Right. The opposite process would release 81.2 kilojoules. Good. Okay. So that's one of the things that's interesting about phase changes. They oppose one another. We have these processes that are opposite one another, right? Okay. So the heat of vaporization of water is really pretty high. By contrast, let's look at the opposite process. Or pardon me, let me mention something else about water. For water, the heat of melting or fusion for water is 6.02 kilojoules per mole. And let me do some rough examples with that. Melting a mole of water requires absorbing about 6 kilojoules. How much energy would be absorbed if you melt 2 moles of water? Good. Okay. And if you freeze 2 moles of water, 12 kilojoules is released. So those processes are the opposite. What happens to temperature during a phase change? By the way, it might be an interesting result. Well, okay. Now, that's true. I mean, you're right. We could, okay. Let's look. Did my calculations include temperature in the formula? They had a constant times the number of moles, right?
Good. Consider the process of boiling water. As liquid water is transformed to steam at 1 atmosphere pressure, the temperature stays complete, it stays constant. Yeah. And during any phase change, temperature remains constant. The energy is associated with changing the phase, not changing the temperature. Okay. So my last part of this chapter is to show how to do calculations in other circumstances when temperature is changing. And for this, we use the basic calorimetry equation. And I'm going to certainly show that on screen here. Okay. So here is the basic calorimetry equation. Let's refresh this thing for a moment. Okay, for the basic calorimetry equation, physicists like to use the symbol Q for heat. And what we're going to use here is that Q equals S. I'll define S, M, and delta T in just a moment. We can use that little triangle thing to represent that. Okay, and some things about these symbols. Let's make this a little smaller. Q is the symbol for heat, normally measured in calories, joules, or kcal, or kilojoules. It's worth knowing that a calorie is equal to 4.184 joules. So a kcal is equal to 4.184 kilojoules. You've probably heard of calories before because we use them for food. S is specific heat. And it measures how difficult it is to heat a substance. And liquid water is 1 cal per gram per degree C. M is the mass, normally measured in grams. And delta T is the change in temperature. It's always going to be your final minus your initial temperature. So this is worth some emphasis. It's used very frequently. Before we do calculations, let's talk about specific heat. Students should know that the specific heat of liquid water is 1 cal per gram degree C near room temperature. Let's compare that to the specific heat of copper. Would the specific heat of copper be more or less than that of water? Think about metals like copper, aluminum. Good, good. Okay, metals tend to have low specific heat capacities because metals heat up very readily. Non-metals like water tend to have higher specific heat capacities, right? Okay, we probably have some problems that we could work based on the idea of the basic calorimetry equation. Let's see if I can go to some of those there. Here it is. Okay. We will be closing out this chapter with some problems. About the basic calorimetry equation. And we have an example on the board. In this example, we want to calculate how many calories are needed to heat a pot of 1,600 grams of water. We're going to heat from 25 to 100 degrees C. Which variable are we solving for? And don't worry, you guys will get a break soon. Which variable are we solving for? Okay, good. Okay. We're solving for calories, which are specific heat. So we need to know the specific heat of water, which is stated at the bottom of the screen. We know the mass, and let's look at the change in temperature. Final is 100, initial is 25. So if you take the difference, it's 75 degrees C. Hang on, let me just close the door here. Okay. So if we write the equation, you can see the setup here, and you can see how the units are going to cancel when we use the equation. Calories are going to cancel. Okay, no, degrees C and grams are going to cancel. Okay, so we're going to go to the next slide. Okay. Solve the equation. 1,600 grams, 75 degrees C. Notice that the temperature change is often your limiting factor in how much you can do. Specific heat cancels. And notice that your answer is 1.2 times 10 to the 5th calories. Calories are not a very large unit of energy. what would this answer be if we converted to kilocalories? And incidentally, food calories are kilocalories. Okay, let's check. Okay. Okay, a calorie, let's see. There are 1,000 calories. Let's just write it this way. Per kilocalorie. Okay, let's get rid of 3 of them. Those 3 zeros. Okay, and what would our answer be? Seems like this is freezing up, by the way. Okay. Students, I appreciate your patience as we come back from break. Okay, and let's check. Do you have video and audio? We're going to be our last part of the period here. Let's check this. Good, good. Okay. As we finish this chapter, I have chosen 4 different calorimetry problems that we're going to be doing. Of them, I would say that number 3 is going to be the toughest for us. But let's see if we can kind of talk our way through some of these. Okay, our first one reads as follows. How much energy is needed to change the temperature of 50.0 grams of water by 15.0 degrees C? So if we do this problem, let's see something. We saw before that the heat Q is equal to the specific heat capacity, in this case of water, times its mass, times its, let's call it delta T, which is the change in temperature. So to calculate the energy, okay, I want to remember here that water is 1, and that's in calories per gram degree C. Let's make this a little larger here. I'm gonna finish the units there in just a moment. I'll have a different way of putting them in there. I am then going to put in, okay, I better make my letters a little bit smaller. Mass is going to be 50.0 grams. And your change in temperature is 15.0 degrees C. So with my marker here, let's put in these units down here are grams per degree C. And let's look at canceling some of the units there. Okay, that's going to cancel, and grams are going to cancel. And the numbers here are going to work out pretty easily. Can you tell me, just by multiplying those together, what you're going to get as your result there? 1 times 50 times 15 is? How many calories? Good. Okay. So that's a pretty straightforward problem. A lot of these are pretty straightforward. So let's contrast it to problem number 2. Problem number 2 says how many grams of water, and all of a sudden this is telling me, hey, I got to think about mass. How many grams of water can be heated from 20.0 to 75 degrees C using this number of joules? So what I'm going to be thinking here, again, I have to use that heat Q is going to equal specific heat capacity times mass times change in temperature. I need to do a little dividing through because I want to solve for M. If I divide the equation through, mass is got to be equal to Q over S and delta T. So on the top there, I'm going to put my number of joules. And then on the bottom, I will put, let me see, specific heat of water is 1 gram, 1 cal per gram degree C. And also in the bottom, I've got to put the change in temperature. We want to put final minus initial. So I'm going to put 75 minus 20.0. That's going to be in degrees C.
we want to do some cancellations here, like cancel this. Let's see. Now I see another problem here. I've got to make my units consistent. So if I want to cancel calories, let's change this up. A joule is 4.184 calories, according to the way it's defined. Let's do some more cancellations. Okay, calories are going to cancel. Joules are going to cancel. And notice that with the grams, if you were to multiply by grams top and bottom, this is going to cancel and you're going to come out in units of grams. But I've got to give some thought to the significant figures. I've got numbers with 4 and 3 significant figures, but notice that this number can only be done to the nearest degree, and it will only have 2 significant figures. So I'm going to get ready to calculate that. 4.184 divide by 1 divide by 55. Okay, and this is going to give us our answer. Let me see. And what is my mass in grams? Let's see something here. Okay, something looks like it's got to be a miss. Oh, my bad. I missed something. 12,500.0. Okay, let's express that. Yeah. Okay, 12,500 times 4.184 divide by 1 divide by 55. Okay, what would our answer be to 2 significant figures? And I want to emphasize, I had just left something out. Now I have the mass times specific heat capacity. I've done the conversion of energy units, and I divided by delta T. Our mass in grams will be how much? Uh, 950. Yeah, other things. Okay, 950, because that would be 2 sig figs the way it's written. Good, good. Okay, let's take questions on that one. That's the second of 4. Okay. We got 2 more to go. Let's show the other ones.
Oh, it's funny. I can see myself working on the whiteboard. Okay. Here's number 3. Number 3 says find the final temperature after 840 joules is absorbed by 10 grams of water at 25 degrees C. Now, you might say we're solving for delta T. We are solving for delta T, but then we've got to think about the final temperature. So if you're doing problem number 3, remember that change in temperature, delta T, equals T final, I'm going to write that as TF, minus T initial. So T final is going to be T initial plus delta T. And if we go a step further, remember from the basic calorimetry equation that heat equals specific heat capacity times mass times delta T. Okay. For number 3, what do we solve for first? Okay, let me think though. Oh, okay, but we know we've got 840 joules. We know the specific heat capacity for water. Do we know the mass? We know the mass, right? So the first thing we would solve for is the good. Okay, so delta T, if we rearrange the equation, is going to be equal to Q over specific heat capacity and mass. So I'm going to make this 840 joules. We're dividing by 1 calorie per gram degree C. And the mass there is 10.0 grams. Let's do some cancellations here. Yeah, you've got the same kind of problem here because you've got calories here and joules here. Okay. Let me think about this. A joule, there are 4.184 joules per calorie. Okay. And let's get our cancellations going here. Yeah, one of the things I could have done is just used 4.184 joules per gram degree C. That would have worked too. You can see that my answer is going to come out in degrees C. So as I get ready to go to the calculator, let me write down what I have to compute. I'm going to compute 840, divide by 4.184. We divide by 1, and also divide by 10. If you look here at this 840, that should be 2 significant figures. So 840 okay, and let's get our answer. We want to get our answer to the appropriate number of significant figures. Delta T
is 20 degrees C. There's a 20 degrees C temperature change. Okay, so, now what is the final temperature? Good. Okay, that makes sense, right? And let's think about the sign convention. The energy was absorbed, so it makes sense that it's going to be hotter, right? Okay, very good. That's one of the harder ones, right? Now let's clean up this slide a bit. And we're going to go do the last problem. This is kind of a fun part. Huh. Here we go. Here's where we want to go. Oh, I do want to clean this up a little bit. Gosh darn it. Yay, I think this is finally working. Okay, here's our last one. And as we finish this chapter, heat capacity of aluminum is 0.9 joules per gram degree C. If we wanted to find energy required, okay, we start with Q. Find the energy needed to raise the temperature of this mass of aluminum. You know, aluminum has a different heat capacity than water. It's going to be 0.9. And notice that they gave it in joules per gram degree C. And then the mass is 8.50 times 10 to the second. That's in grams. Notice our units all have to be consistent. And for your change in temperature, your final is 94.6 and your initial was 22.8. Notice that your temperature change is going to be the nearest tenth. And let's also look at canceling out some of the units. Like that's going to cancel and that's going to cancel. And I'm going to take this over to my calculator. Let's look at the temperature change first, because if you had 94.6 minus 22.8, that's going to be three significant figures. And my calculation will be 0.9, 8.50 times 10 to the second. And the last thing here is 94.6 minus 22.8. And let's think about this number. Let's think about it significant figures in units. How many sig figures should there be in the answer?
Okay, good. One way to write the answer then might be 5.50 times 10 to the fourth. And the units are in joules. We mentioned before, a joule is not a very large unit. So it's entirely possible, rather than writing it that way, you might want to write it as 55.0 kilojoules would be another way to write it. Or actually, it would be 54.9 kilojoules. And that is what we're doing on this chapter. So I am looking for your questions as we kind of clear out of what we're doing in this chapter and go on to the next chapter, right? Okay, because we've been taking a good look at gases and liquids and solids and things like that. And we're about to go into our next chapter. Okay, can you watch, switch screens? Yes, yeah, let's do that. Yeah, and one of the things too, although students can view recordings, you might want to take a picture of this, for example. In the shared notes, I'm also going to show you the source of these problems. So sometime when you're looking at the recordings, you might want to look at the shared notes. And let's move this around a little bit so you can see it better. Okay. So as we get ready to transition into the next chapter, which is chapter 8, chapter 8 would be something that we're going to look at today, and obviously we're going to be spending more time on next time. Let's look at something here. Okay. This is all about things like mixtures. And mixtures are very commonly encountered in everyday life. And we've discussed solids, liquids, and gases, and mixtures can have any of those things in them. So what are some mixtures you might find in your home? After all of us are home all the time because of this social distancing, so okay, yeah, like dressings, like salad dressings, good. Okay, is milk a mixture, by the way? How about soda? Yeah. One of the reasons mixtures are so important is that most of the things that we encounter in everyday life are not pure substances. Most of them are mixtures. And as you might guess, let's try and develop the distinction a little bit. Elements, something you would find on the periodic table, those are pure substances. A pure compound, a compound just by itself is also a pure substance. However, most of the substances that we encounter in everyday life are a mixture, and in a mixture, the parts of the mixture don't have to be chemically bonded together. The parts of the mixture can have a lot or a little. You can make mixtures with a lot or a little of a component. Let me give another example for a mixture. Say that you made a comparison between wine and vodka. Both of them contain alcohol and water, but which contains a greater fraction of alcohol, wine or vodka? Probably everybody's going to eat vodka after all this quarantine, right? Okay, so it makes the point, because the different parts don't have to be chemically bonded together, you can put them in different amounts. Now, how about coffee? What about strong or weak coffee? Which one has more coffee grounds in it? The one that has more coffee grounds is the one that is. And again, probably all of us, I would assume, need lots of coffee because of this lockdown. Good. Okay. Now, another thing about mixtures too is that they can be what are called heterogeneous or homogeneous. And with a heterogeneous mixture, it doesn't look the same throughout. Its composition, based on what we can see, is not uniform. And an example of a heterogeneous mixture, I can get you a very obvious one here that a lot of people like. One of my kids ordered it last night. Don't let me give you any ideas. But if you look at a pizza, for example, okay, this part of the pizza is dough. This is the pepperoni. This is the crust. It doesn't have a uniform composition according to what you can see. And let's also look at ice cream for the moment. Yum, yum. Okay, if you were to look at ice cream can be a heterogeneous mixture because the composition is a little bit different. You have the ice cream part, the nuts, the chocolate. So from what we can see, it's not evenly distributed. Now that I've got everybody hungry, let's look at salt water, which probably doesn't sound as appetizing. If you look at this salt water that we're showing here, once the salt goes in, it looks the same throughout. So if the mixture looks evenly distributed, we call it homogeneous or a solution. And how about sugar water? Would sugar water be homogeneous or heterogeneous? Sugar water would be good. Okay. Yeah, so if it dissolves fully and all that kind of stuff, it would be homogeneous. Let's switch back to this whiteboard for a moment. Okay. Now, keep in mind here, and we're going to finish about 9:05, so not too much longer. When we have a solution, it's a homogeneous mixture with small particles. If it's a liquid, it should be transparent. That doesn't necessarily mean it's clear because some liquid solutions have a color, but it should be something that you could that's transparent. And a solution has two parts. Your solute is the substance that's present in the smaller amount, and the solvent in the greater amount. You won't be surprised to know that many of the solutions that we talk about every day contain water, and those are called aqueous. So we're obviously going to have a big focus on aqueous solutions as one of the things that we look at. And okay, here are some further examples of solutions that we see in everyday life. You breathe in air. Air is mostly nitrogen gas with some oxygen gas and smaller amounts of other substances. So notice that it's possible to have a solution that's two gases. It's also possible to have a solution where the solvent is a liquid, like water. If you are being given a saline solution, you have a solid in a liquid. You could have a liquid in a liquid, like alcohol and water. Now, surprisingly to many people, you can have a solution where the solvent is a solid. And you can see this dental filling that you have some mercury and silver, which originally they were mixed when they were liquid, but then they were solidified. So you can have solid mixtures. All of these things are possible. Okay. And we'll also be seeing in an upcoming lab that there's something we can call a colloid or a suspension. These are mixtures that are not quite true solutions. When you do the lab about a colloid is a homogeneous mixture, but the particles are larger than they would be in a solution, and they're often opaque. You can't filter or settle out the particles in a colloid. And again, you're going to be doing an upcoming experiment about those. Larger still is when you have a suspension. This has large particles. We consider it heterogeneous rather than homogeneous. It's not really dissolved. You could filter these away. And so let me also show examples of these. I'm going to show an image that shows the difference between a colloid and a suspension. It has to, we can tell the difference with it using what's called a Tyndall test. And you're going to see that in lab soon. So when you look at the picture on the far right, if you have a solution and you try to pass a beam of light, the beam of light goes right through because the particles are small. On the other hand, if you pass it through a colloid, because the particles are larger, you are going to see the light beam. You'll actually see the light beam in the liquid. It doesn't just pass through. Milk, incidentally, is a colloid. And with a suspension, that Tyndall effect, as we call it, will be greater still. And you're going to see that when we do one of the upcoming labs. And let's return to our last few concepts here. Okay. This table summarizes the difference between them, differences in size, and whether the components can be filtered out or not. So again, I kind of highlight that for the upcoming experiment that you're going to be doing on colloids. And let's see where we're going to be kind of ending up here. I think the last thing that I would mention today, a point that we're going to be taking up later as we go to the next lecture, is that it is important to know that in solutions, sometimes you have charged particles in the solution. If you put a salt in water, it's going to be able to conduct a charge, and that's what we call an electrolyte. If you are a nursing student, you could probably know that there are substances like sodium and chloride ions that conduct electricity in the body. Other substances which dissolve as molecules will not conduct electricity. So electrolyte and a non-electrolyte behavior is what we're going to be studying next as we go to chapter 8. This brings us as we finish here, we are just starting 8.2. And again, this is all about mixtures. And we have had a good session here. We can see, obviously, when you look at the announcements and look at what we're doing next, you can see that when we meet again, we're going to be proceeding more into the Chapter 8 and Chapter 9. And it's my job to keep you up to date on, where we are. We're just starting 8.2, so you can see more of Chapter 8 and then Chapter 9 as we work next time. Keep in mind that our class still has a good number of meetings. This is the 23rd. We've got the 30th. Our final exam is very early in June, so we still have some meeting time. I know that some of you may prefer to although you can ask questions here, some of you may prefer to email or text me when you have questions about things. So let me take any final questions that might need to be answered in class. And I appreciate your patience with everything here. You can see that I'm working hard to find ways that, to have their meetings work well. I would anticipate the meeting after next. And keep in mind, I don't have to do the exams at the class meetings. We can have them taken outside of class meetings if desired. So I would say, let me think. If today is the 23rd and the 30th, I believe it may be, let me think. It will occur sometime after our next class meeting, and it would likely be given outside of class. Okay, let me see if that answers. So I wouldn't say so much that we have an exam date, but what I'm thinking is after we're finished with 8 and 9, then I can give the exam, and most likely I'm going to do it in outside of class time. Okay.
Professor?
Yeah.
Oh. So our next test is going to be on the 30th?
It will definitely not be at the class meeting on the 30th. And if we were to finish chapters 8 and 9, I may already have the review material for the practice material for exam 3, or if not, I could do it very easily. So it will not be on the 30th. But as soon as we finish chapter 8 and 9, we can start thinking about that. And let's think of something here. I think it is likely that I would give the exam in outside of class time. And so an answer to the question would be, it will not be, I know that it will not be during the meeting on April 30th. It will not be during that meeting. However, it could be assigned after we have finished chapters 8 and 9, and it can be assigned outside of class time. Yeah.
So the date is to be determined then.
Yes, and it will not be during it will not occur during our April 30th meeting. It could occur after that, and most likely in outside of class time. Now, something to be considered is whether you would prefer to have the exams be in or out of. I'd be willing to hear students a little bit if you want to discuss whether it should be taken, in class time or outside of class time. And incidentally, it could be taken in what we call the lab time too. I think that the biggest thing is if students are taking exams, one of the things is it's probably best if students take exams during a time when I might be awake if there was a problem with it. So, I think a good way to look at it is early May is what we're thinking about. And obviously it has to be taken online. It would be done as a quiz style in Canvas, the same as the other one. Okay, so let me think. That's what I can tell you so far. Okay, and send me questions and things like that. And I also, if it's taken outside of class, I would probably provide some range of days, for students to take it. In other words, they don't have to take it an exact time, but I would say within this time interval, But I've got to have chapter 8 and 9 done for that. Okay. Yeah, I got that. And one of the nice things too is that, you know, I can see everybody, you know, as participants. Okay. So as soon as their recording is ready, they keep recordings on this server for 14 days. And so one of the things, as soon as the recording is ready, I want to convert it and then make it available to you guys. Okay. Thank you. Thank you so much, everybody. Okay. Thanks. And I will see you guys online. Right? Okay. Stay safe, right? Be safe. Okay. Bye, everybody.